Hello, everybody. This is Professor Ma, and this is the section on Taylor expansions. Okay, in last sections, we talked about the functions, and that's infinite differentiables, and we look at the point at x equal to 0, and we want to come up with polynomials approximate this function around a very small region around x equals 0. So we first find the first degree polynomial, which is the line. Now we find the second degree polynomial, which is a parabola. Now we find the third degree polynomial, which in this case, I'm not quite sure what exactly how it fits, probably fits something like that. And as we keep doing this, the polynomial and the sequence of polynomials, which we call Maclaurin polynomials, gets look like closer and closer to the red curves, the original formula. Now we're going to talk about the polynomial approximation at some other locations, maybe over here at x equal to a. Okay, so we're going to find the formulas that, the first degree formula, the parabola, and the third degree formula that approximate at that point. And in particular, we're going to write formulas, polynomial formulas in a special manner, which we say is based at the point x equal to 8, not x equal to 0, x equal to 8. So and these type of expansions are called Taylor expansions, okay, as opposed to 0, which is max expansions. Okay. We have these Maclaurin expansions, again, is at 0 first degree. So if I have a polynomial in x, and then the first degree part approximates a straight line, the first 2 degree approximate is an approximation of a second degree, quadratic approximation, if you like, of the original curve. And then the third is the third degree Maclaurin series is a third degree approximation of the original curve. And of course, in this case, the fourth degree is the original problem, the polynomial, okay? And now we're shifting to another point. Okay, now what happens if I'm looking at the same polynomial in the version that's around 0, but I'm gonna shift the focus to this fourth degree polynomial at the points x equal to 1. Okay, and in particular, the way we're going to write these formulas as a polynomials in x minus 1. Okay, so it's a 4 degree x minus 1 cube, etc. Okay, and this polynomial is called the Taylor polynomial of P of x, the Taylor versions. Notice these two polynomial are exactly the same polynomial, okay, except the way they express them is different. This one we say is based at x minus 1 or based at x equal to 1. And this one is based at x equal to 0. Okay. And don't get these two mixed up, because to the following, this is not a formula where I plug in minus 1. And if you remember in shifting graph, if I were to plug in minus 1, I will get, I will get a formula that actually shift the entire graph to the right, 1 over. So and that would be a totally different graph, okay? We're not talking about shifting the graph, but what we are saying is that the polynomial can be written in x or in x minus 1. And that's the one in x minus 1 is the one that we are going to calculate how we get that. Okay. And notice if I have a series of x minus 1, these are first degree equations in x minus 1 written that way, then that's a linear polynomial approximate at 1. And if I write a quadratic versions of this base x minus 1 polynomial, then it's a second degree approximations at x equal to 1. And then x minus 1, if I write that as a third degree one, and then that will be this one. Okay, so these three x minus 1 based polynomial are the approximation at the point x equal to 1. Okay. And the reason that they approximate again is that if I choose a number that's very close to x equal to 1, I say if I want to evaluate x 0.1, when I plug it in, I wind up with 0.01 to the 4th power, and this is really negligible. In other words, if something very close to 1, then the higher degree ones actually is negligible compared to the formal ones. And the higher degree one just make the accuracy a little better, little better, little better. Okay. And we call this the Taylor polynomial at x equal to 1 of original p to the x. Okay. And here's the formula of the Taylor, how do you create a Taylor polynomial base at x at a, which is a polynomial in the expressions of x minus a. And the reason is exactly the same as before for the Maclaurin series. Basically, you cancel divide by the n factorial to cancel that when you take the derivative, the power comes down and they multiply as you keep taking derivatives. So you have to remove those n factorial when you keep taking derivative to get to the original coefficients. Okay. Okay, so let me remind you, Maclaurin series is the regular versions, polynomial based in x, but Taylor polynomial expansion is based at x minus 8. Okay, and this, what I meant by that is these versions is the Taylor expansions. Okay. Oh, by the way, and these two are exactly the same polynomial. Okay. If I expand the top one and write everything in x, then it should come out to be the same as Maclaurin series. Okay, same formula written different way. So here's an example of approximating 1 plus x squared. Well, not approximating, right into a polynomial as x minus 1. So I want it written in this version, basing x minus 1 square and x minus 1. So everything is x minus 1, x minus 1, x minus 1 cube in terms of x squared, x cube. Okay. And this is how we do it. Go by the Taylor formulas, and you take the first derivatives. You plug in 1 first, then you find the first derivative, plug in the first derivatives at 1. Calculate second derivative, plug in the second derivatives at 1, and the third derivative beyond 0. So when you formulate the Taylor polynomials, it stops right here, 2, right? So you plug in this number, and when you write the polynomial expansion, you write x minus 1 square, x, okay? And you put a 3 and a 2, 3, 3, 2. Put these numbers 3, 3, 2 in respectively what these primes are, and that's it. Okay, and then what you wind up is a little bit more complicated looking 1 plus x squared. Okay. But there's a point, so we can do that. There's a reason we do that. Okay, so where's that polynomial again? Yeah, so these are the versions that where the polynomial is x minus 1. And these polynomials down here will approximate these second degree functions at 1. Here's another way to calculate it, so I can let you read it. Basically, this is only work if you are working with a polynomial of small degrees. And if you don't want to take that many derivatives, you can directly match the format. Say, hey, what I need for A number, B number, C, and you can compare coefficient on sides and step by step to recover each number you will need for the A and B and C. Okay, so these are the Taylor and Mac and Taylor polynomial. And here are some Taylor expansions, and this particular one is for cosine x at pi over 2, okay? And so we're going to need to take derivative of cosine x, so it goes in cycle, cosine minus sine, minus cosine, sine, and that goes around. When you plug in pi over 2, you get 0 minus 1, 0, 1. These coefficients is going to go in front of x minus pi over 2 to a power. Okay, depending on which one you cycle in the cycle. Okay, and so this is the Taylor polynomial expansions. Okay, and then is there any way to write this in a closed form? In other words, is it impossible for me to write this as some sort of an times x minus pi over 2 to the nth power? And is any way to write this cycling 0 minus 1 to 0 to 1 to 0 in a nice formula? Actually, there is. Okay, so this is kind of interesting trick. Okay, look at the formula for minus sine x. Okay, and if I look at this formula and plug in different integers, when n is 0, well, round to the index, when n is 0, I get 0. When n is 1, negative sine pi over 2 is negative 1. Sine pi over 2 is 1. So this formula gives exactly this pattern's formula. What? 0 minus 1, 0, 1. So this I can use as a coefficient for the Taylor expansions. Okay, so I can stick that in the front for the Taylor expansion. That's for the alternating for the sine for the coefficient go in the fourth cycle. Okay, remember plus minus 1 ratio of power going 2 cycle. 1 minus 1 plus 1 minus 1 minus plus 1, and here's a fourth cycle formula. Okay, sine of m pi over 2. Okay. Log of x is not defined as 0, but we can find a series polynomial around 1. So here's a picture of log of x. Okay, so I want to know, okay, what's the polynomial or the Taylor polynomial for the linear approximation? Then what happens if I were to approximate with a parabola? Oops, well, something like that. And how about even better if what happens if I approximate with a third degree functions? Okay, so how do I calculate those approximations at 1? And Taylor polynomial. Take the first derivative of log x, second derivative, third derivative, and fourth derivative, and so on and so on. And then a patterning merge. What's a pattern? I'm given as the coefficient, as the power multiplied to the front, when I take the derivative, they form factorial. If I do it again, I'm going to get 5 factorial in the front. Okay, if I do f of 6, I'm going to wind up with this number is 5 factorial. And the second thing, there's a sign swap, plus minus, plus minus. So I have to take into consideration writing a formula that's n factorial, but at the same time is plus minus n factorial. And so if after you're thinking about for a while, this is it. Okay. So this is the nth derivative. And now I want to plug in 1. And of course, when I plug in 1, I just get n minus 1 factorial times whatever signs in the front. Okay. And put everything. So this is what happened if I plug in 1. Then I put this in front of x minus 1 polynomial, x minus 1, x minus 1 squared, x minus 1 cubed. Okay, so, but the factorial cancels out. So I want a very clean formula. And if I write it out explicitly, this is the Taylor polynomial or the Taylor series of infinite degree polynomials that are approximating x equal to 1. I'm not approximating. Okay, oh, yeah, approximating, but the not, you will see shortly. Okay, this doesn't work for every x. Okay, there's only a limited range because this is a power series and this is has a convergence radius of converging. You will see later on the label if you calculate it. Actually, it's a good homework. It is a radius converging of this is 1. Okay. In particular, it's very interesting what happens if I plug in 2, x equal to 2. So in other words, what we have is this series of polynomial, they get closer and closer and so on and so on. A third-degree polynomial fits better and better, but they only work up to around the boundary of radius equal to 1. Okay, they only work for this point around there. Of course, 0, there's nothing to talk about 0. But it's interesting at what happened at this boundary. That's when x equal to 2. So if I plug x equal to 2 into this series, I get 2 minus 1 is 1. So I get the alternating harmonic series actually add up to be plugging 2 for x is log 2. So that's how we get the value of log of 2. I mean, that's, oh, yes, and that's how alternating harmonic series, we know it converges. Why? Because the decrease go to 0 and it switches sign. And so it converges log of 2. But on the other hand, if I put absolute value, if I use all pluses, it diverges because it's harmonic. So this convergence is conditional. Okay, and that's an interesting fact. And so this is Taylor expansions. Okay, and that's it. Bye-bye.